Hi, my name is Murthy Upmaka. I'm a Solutions Engineering Fellow at Keysight Technologies. In this video, I will discuss the active impedance in phased arrays when all the elements are connected with load-pull amplifier models. We will see the significance of active impedance, the challenges, and the solutions. Let us begin with a very simple phased array with 4 elements as shown here. If we electromagnetically simulate this structure, we will get the element patterns, which we call embedded element patterns, of each one of these microstrip patches, as well as the S matrix. If we look at this structure, each one of these patches is an independent one-port network. But how come we got a 4-port S matrix as an output? There is no wired connection between these patches. So the cross terms should not be there. The cross terms are there because they are coupled through what we call radiative coupling. If we apply voltages V1, V2, V3, V4 at ports P1, P2, P3, and P4, we can write the reflection at port P1 as V1 star S11. This is true only if the cross terms S12, S13, and S14 are negligible. If they are not negligible and are significant, then we have to modify the equation to be V1 S11 plus V2 S12 plus V3 S13 plus V4 S14. This phenomenon, this modification of the impedance or the reflection is what we call active reflection or active impedance. This happens only in phased arrays. We can write this similar reflection equations at P2, P3, and P4 as well. All of these reflections, as we can see, depend not only the reflection coefficient at that port, but also on the cross terms in the S matrix. They also depend on the incident voltage, not just the incident voltage at that port, but the incident voltages at other ports. Another interesting phenomenon here is, as we steer the beam, we are changing V1, V2, V3, V4 phases. In other words, we are changing V1, V2, V3, and V4. If we change V1, V2, V3, and V4, the reflections at those ports will also change. In other words, the impedances looking into these ports will change as we steer the beam. Let us take a simple phased array subsystem as shown here. We have 4 programmable attenuators, 4 phase shifters, 4 amplifiers connected to our 4-element patch antenna array. All these amplifiers will see different impedances as we steer the beam. While the reflection at P1, P2, P3, and P4 are different for a given angle, these reflections or these impedances experienced by the amplifiers will change as we steer the beam. This will bring in some challenges to the phased array designer. Challenge number 1. We intended to supply the voltages V1, V2, and V3, V4 with a desired phase shift of phi 1, phi 2, phi 3, phi 4 that steers the beam in a specific direction. But because of this phenomenon of active impedance and also, of course, the insertion phases may not be exactly identical for all the four amplifiers, we will not get exactly the desired phase distribution at the ports of the antennas. The interaction between the amplifiers and the antenna elements will come to a steady state with a different phase distribution. That means when these four elements radiate, they are not going to give us the exact direction of the beam which we wanted. Another challenge is because of the modification of the amplitude distribution because of this active load phenomenon. That means we are not going to be able to get exactly the same desired, expected side lobe performance in the far field. As we can see, the impedances keep changing. The impedances experienced by these four amplifiers will be changing as we steer the beams. Even though the power amplifier designer might have done a good match between the amplifiers to a specific set of impedances, if these changing impedances range over large values, they may not be able to match with all those impedances. That means amplifiers may not be well matched across the performance range of the phased array, which means the energy transfer from amplifier to the antenna elements will not be optimal or will not be maximum. Another last challenge is for extreme cases of, let us say, the reflection coming from a specific port into the amplifier connected to it is large enough to degrade the performance of the amplifier. This is by far the most serious consequence of an active impedance phenomenon. So what do we do? What should the phased array designer do? Before looking for solutions, we should be able to simulate this phenomenon. It's not very efficient to fabricate the amplifiers, connect them to the array, take them to the anechoic chamber to test them. That will be too expensive. So we want to do everything in the simulation, in the design phase. So the step number one is to be able to get a very accurate model of the amplifier while the load is changing. Fortunately, the X parameter modeling of the power amplifiers is very conducive to varying loads, and we can extract such model either from a circuit simulator like Advanced Design System, a Keysight product, or a network analyzer, professional network analyzer PNA-X, again a product of Keysight. Either way, the X parameter load pulled model can be brought into SystemVue and can be connected to the antenna array as shown here. Starting with 2023, one would be able to pretty accurately simulate the load pull effect of a setup shown here. So we can simulate the steady state Z load that is settled down after the interaction between amplifiers to the antenna elements happened. How do we know the Z load predicted by the simulator is accurate, by the system simulator is accurate? We always consider circuit simulators like Advanced Design System as golden standard because they start with the device models and they have very powerful techniques like transient spice or harmonic balance techniques to predict the complex voltages and currents in a network. As we can see in the ADS design, we connected the electronics, including the load pulled X parameter model, to the S parameter matrix of the antenna array. After simulation, we can predict the impedances looked or experienced by the amplifiers looking into the S matrix. On the right-hand side, we can see that our prediction from circuit simulator and system level simulator agree pretty accurately. So with this in hand, can we now find solutions to improve the performance that was degraded initially by the active impedance phenomenon? In a phased array system, we have the control on the phase and amplitude, which we usually use to steer the beam to control the side lobe levels. We can, in addition, take advantage of this flexibility to re-establish, to re-optimize, to get the phase distribution and amplitude distribution at the antenna array. An optimization routine can be run based on the phased array designer's own intellectual property, and the phase and amplitude distributions can be established that will give a good match between the amplifiers and the antenna array. As a result, the far field will be what is expected. So in this video, we have seen the concept of active impedance, the challenges the active impedance brings in, which are compounded by the load pull amplifier behavior. And finally, we have seen how to predict the behavior in a simulator, system level simulator. And finally, after that, we discussed a solution to be able to counter the problem. I hope you enjoyed the video. Thank you very much for watching this video.